Hello and welcome to this lecture on an introduction to the design process. As we know, the design process is complicated. It involves so many other aspects, aesthetics, economics, safety, reliability, and so on. We will be looking at this design process from a mechanical engineering standpoint. Um, so first, we're going to talk about what is design. Design is identifying a need and then formulating a plan to reach that need. That's as simple as that. And in going to that goal, we need to satisfy a number of constraints related to economics, safety, reliability, public safety, and competitiveness, ability to manufacture, and so on. So there's a number of things that we need to consider in the design process. So if we look at mechanical engineering design, it follows all of the design steps that are usually obeyed in a general design setting, whether you're designing a system, designing for aesthetics, and so forth. So let's focus on mechanical component design. So I identify a need. Let's say that I need to design a gear box, gear speed reducer. So that's my need, and I have a certain amount of horsepower, and I need to do this job. So once I identify the need, I need to formulate now a plan. Plan means a process. So I need to define the problem itself. So I want to say, well, I have this horsepower. I need to have one input shaft, one output shaft, and a counter shaft, and I need to have gears, and I have to have a structure, and so on. So I define my objective as far as the problem is concerned. Once I define it, then I move to the next step. What's next? Next is to do analysis. So analysis requires a lot of tools, mathematical tools, mechanics, and so on. And then after the step, I can do iterations, and then I go into the next step, which is synthesis. So I go to every little piece, and I kind of go into detail of how to design each gear, each retaining ring, each key, each ball bearing, and so on. So that's kind of synthesis. Sometimes I cannot meet the design requirements, and I have to do more iterations until I reach the final solution. And when my design is completed, then I need to optimize it with an optimization, going back and forth until it meets the requirement. And finally, we will have to evaluate it either by giving a presentation to the public or to the reviewers or to the licensing body that will certify the product, and so on. So it is shown here in this example where you have identification of the need, definition of the problem, then you go through synthesis, step, analysis and optimization, evaluation, and then finally presentation. And you can see there are levels of iterations on each step, as you can see in here. So next in the design process that we have to consider many different considerations when we design a component. We consider not only the cost and ability to manufacture it and assemble it, but more often we consider aspects like aesthetics, like functionality, like product liability, reliability of the product, functionality, many different things, weights, and so on. Generally, we don't have to go through this extensive list that you see here. Like you can see 26 different possibilities for characteristics, because that all depends on what are we designing. So we may be able to select a number of those characteristics and satisfy them. And now when we do the synthesis and analysis part, we require tools, and that's what we're going to learn in this class. We're going to learn tools of the trade. So we will learn how to look up tables and how to look at material selection and how to find preferred sizes and information of that sort. And also we will learn the mathematics behind the mechanics for finding stress, strain, deflection, buckling, and so on. And a lot of times we'll find that some of these analytical tools must be programmed in computer programs. So we'll learn MATLAB, and we will use it to design deflection, finite element code for deflection of shafts. And also, we would need to learn some of the advanced tools to visualize the component and design the size, and that is computer-aided design tools like SolidWorks, for example, is going to be our one of the main software pieces that we'll use. And we could also use SolidWorks to do certain levels of finite element analysis, elastic, for example, or we could do thermal. But more often we're going to also practice on using other finite element codes like COMSOL and like ANSYS. So we will use all of these tools to build our ability to do the synthesis and analysis and optimization process. As far as the material data is concerned, we have a bunch of libraries, government sources, and other professional societies that can provide us with material data, and also we have quite a bit of information on the internet. So if you look on the internet, there's a website, globalspec.com, and that has specs on gears and shafts and pulleys and flywheels and so forth. So we are obliged to use these kind of internet sites to give us information on what is available that we can readily pick to make our design. In addition, we have the U.S. Patent Office, USPTO, that is useful to give us ideas about different designs that are similar to what we've been trying to think about, and we could utilize some of this information. Now I move on to another subject, and that is, what is the designer's role in the society? So as a designer, my role is very important because I need to make sure that whatever I'm designing does not harm the public. So I need to be competent, review my information, keep learning, lifelong learning, find network with other designers and other people of similar interests, so we can keep our trade and profession to the highest possible standards. And in doing so, we have a code of ethics that we will abide by, very similar to the code of ethics that other professionals follow, such as doctors, physicians, pharmacists, nurses, and so forth. So our code of ethics is actually articulated by the National Society of Professional Engineers, NSPE, and it has 6 fundamental canons that we should hold safety and health as paramount of the public, and perform services in areas of our competence, not to just go and do a design in electrical engineering while we only know mechanical engineering, for example. And as public, some of us will work as public employees, so we can give truthful statements to the public. And if we work as a consultant, then we just obey the relationship between us and the employer who is employing us. And of course, we avoid deception and conduct ourselves honorably in that process. So this is the creed that we have. We have to pledge our performance and honesty, and that we live according to the laws of man, and that we place our service ahead of profit, and that kind of creed should guide us as engineers, that we will be proud of our profession, proud of ourselves. Next, I move on to the topic of standards and codes. And when we say standard, it means that we have a preferred size for a component, or a preferred finish, or a dimension, or the way that is manufactured, that is standardized across the entire world. And this is the ISO system, that standardization, so that if we have a component that we buy from a certain location or supplier in one country, it will fit immediately in another country if we're given the same kind of conditions. So the standard is a set of specifications on the products themselves, and it achieves uniformity for everybody. On the other hand, when we talk about a code is a set of formulas or rules that are made so that we can obey them in the design process. And if we obey these rules or codes or formulas, then we achieve a certain level of safety and reliability that is guaranteed. Of course, that doesn't release us from the liability, because we have to go through a very detailed process while we're doing the design to gain liability. So in this case, the codes and the standards are established by various organizations. For example, in this course, we will use the American Gear Manufacturers Association, AGMA. So AGMA, they have a set of rules or codes that we will use to select gears and to make sure that they can transfer the power without breaking, and for survival a certain amount of time, and so forth. So that's what we cannot just go and use the code of the Aluminum Association Society, for example. They wouldn't have this particular information. So for every product or groups of products, there's going to be a set of standards put together by an organization, or a set of codes put together by the organization that is closely affiliated with the product. For example, in building very large pressure vessels for nuclear reactors and for other applications, there are codes that are put together by the American Society of Mechanical Engineers, ASME, and the codes are labeled pressure vessel PV-B, pressure vessel and boiler code. And that's like a set voluminous volumes, like maybe 6 or 7 voluminous volumes that we must consider when we design large-scale pressure vessels. So it's not up to us, but we have to kind of practice. And in this course, we will start the process. And as we go on and work in certain applications, we'll gain more and more information and become more and more specialized. So this is the idea of the codes and standards. Now we move on to the next concept in product design. And that's the concept of tolerance. Because when you design a product, then you design it for a particular uncertainty level. In other words, there's nothing that's guaranteed 100%. So if I'm designing a size of 1 meter, it cannot be 1 meter. If I just go get a shaft 1 meter long, I'm not going to find it. It's going to be plus or minus a few millimeters, or maybe plus or minus just a tiny bit. So it's the idea of tolerances. So if you look at tolerance, it has a price. The tighter the tolerance, the more machining steps that we have to take, and the price will go higher and higher for higher levels of tolerance, or for better tolerance, closer tolerances. The other aspect here is that if we are designing a product, I may have the option to select between two different methods. One, for example, could be certain manufacturing steps like hand made, like the labor is more involved in that process, human labor. And then another one that could be more automated. So if I'm comparing these two, consider manufacturing process A and B, I have to consider the startup cost for each one and also the cost per component. And generally, we'll find that there is a break-even point in our selection, depending on the number of units that we produce. So if I look at the idea of tolerances, is the cost versus the tolerance in mils. This is fraction mil, 1,000th of an inch is 1 mil. So for 30 mils tolerance of the surface finish, that is very rough. So the cost is very low. As we increase the precision, we improve the roughness down to 3 mils. The cost increases slowly. And this we will have to turn the surface. Now, if I want to have the surface to have less than 1 mil of roughness, like 0.5 or a quarter of a mil, then I need to grind it, and finally I need to hone it. And you can see that the rise in the cost is quite significant when we get to these very tight tolerances. The next idea is the break-even point, and here I have an example of a option between an automatic production of a screw machine versus hand production of screw machine. The automatic, you can produce faster, but it needs 3 hours of setup. And the screw, you produce less per hour, but you don't need setup. So obviously, the automatic starts from a high setup, like 3 hours times $20, it will be 60, and then it moves at a slower rate, while the hand screw machine doesn't have a setup fee, and it moves at a higher rate. So you get a break-even point. So if you want to produce 50 units and above, the choice is automatic. 50 units and below, or less than 50 units and below, then you choose the hand process. So in this case, we have now talked about the tolerances, and we will get more into that in the future. And I would like to finalize this segment by talking a little bit about the role of uncertainty in the design. We have basically two parameters, one that is related to the material, and the other one that is related to the loading. So the loading can be either a load itself in pounds, or can be the stress that we compute. And the parameter related to the material can be the strength, or can be the maximum load beyond which it collapses, or some other description that, like fracture toughness, for example, that is a property of that material. So the relationship between these two defines the margin of safety that we have. So we're going to define the safety factor as that relationship to deal with the uncertainty. And the safety factor here is defined as the loss of function parameter, such as the load at which the system collapses, or the maximum strength of the material, divided by the maximum allowable parameter, and parameter meaning stress, for example, or it could mean a maximum allowable load. So if I want to, for example, if the loss of function parameter is the ultimate strength, say the ultimate strength is 150 KSI, while I'm allowing only 100 KSI as the maximum stress that I compute, then the safety factor is 150 divided by 100. That gives me 1.5. If I know the safety factor, I can always design for the maximum allowable load or the maximum allowable stress with no issues involved. So to close up this session, we talked about the safety factor as a guarantee to absorb all of the uncertainties, because we are not certain as to the composition of the material or the heat treatment that can produce different variations in the strength. We're also not certain about the load or the dimensions, so can produce different variations in the stresses that we compute. So there's uncertainty both ways, on the material side and on the load side. And we deal with that in a simple way using the safety factor approach. Another approach that is considered these days more often is a reliability approach. And in that case, we consider the distribution function of the strength, the distribution function of the stress, and then somehow we factor that in and find a figure of merit that tells us about the reliability of the component. So what is the probability that the component will survive a certain number of cycles or a certain amount of time. So that will be a subject that we will not touch on because it takes a little bit longer time than what we have in this allowed in the 10 weeks of this course, but we'll focus on the safety factor approach in most of our designs. In the next segment, I'll start showing you examples on calculations for safety factors and how they are applied